Hello everybody. In this video we will discuss about the reaction of aldehyde or ketone. They both will react equally with primary amine. That's important. And you need a trace amount of acid. So what does this mean? You don't need the pH of the solution is not going to be too low or too high. It has to be at the sweet spot. So not a lot of proton, but just enough. Okay, so that's trace amount of acid. We're gonna form imine. So two critical ingredient we will need. One is primary amine, another one is trace amount of acid. Okay, so let's look at so basically what it will do is it will get rid of your water, and then you snap them back all of your nitrogen and carbon. So see, the oxygen and hydrogen is gone, and then you have carbon and nitrogen's joined in. Okay, so that's pretty much all we had. I should have drawn slightly better way. So we could have had like this. Okay, so that's our imine. So this is a very important reactions biologically. Before we jump into the mechanism, let's quickly recap what is a primary amine. A primary amine is, we know that nitrogen can form 3 bonds, right? So when you have all 3 of them are hydrogen, that's your ammonia. When one side is carbon chain, so when one side is carbon chain, but the other 2 are hydrogen, so that's your primary amine. So there is one carbon chain. So if you notice, there is one carbon chain. So nitrogen can always make 3 bonds, just like oxygen can always make 2 bonds. So what if we had 2 carbon chains? If we have R and R, let's call it R1 and R2. They don't have to be equal. And now we have hydrogen. So that is your secondary amine. Okay, secondary amine. And obviously the tertiary amine would be when all 3 of them are carbon chains. So I'm drawing a trigonal pyramidal structures because we know that the structure of the ammonia or amine, any type of amine, are trigonal pyramidal, and all of them will have a lone pair, and this lone pair will serve as a nucleophile or a base. Okay, and this is gonna be our tertiary amine. So just depending upon how many carbon chain it is connected to, we can call it primary, secondary, and tertiary amines. So for this particular reactions, we need primary amines. Okay, so primary amine is where it's connected to 2 hydrogens and 1 carbon chain. When it's connected to 1 carbon chain, that's our primary amines. So let's look at the mechanism of this reactions. So what if we got CH3CO CH3, and then we're gonna react this with NH2CH3. So what this will do is, we know that carbon has delta positive and oxygen is delta negative. So carbon is electrophilic. That means this carbon here loves electron. So it turns out, who has electron? So this nitrogen will serve as a nucleophile. So this would come and attack on this carbonyl carbon. And when it does, what would happen to our pi electron? We will push up. So let's draw the intermediate that we will be forming. It's going to be CH3CO minus CH3. And then we have NHHCH3. And just like we had for oxygen, like remember the tips? When nitrogen has 3 bonds, it's gonna be neutral, like here. When nitrogen has 4 bonds, it's gonna be positive. And when nitrogen has 2 bonds, it's going to be negative. So that's your tips. We had the similar tips for oxygen, right? Okay, so in this case, we have our nitrogen is going to be positive because nitrogen has 4 bonds. Well, it's giving away electrons, so that's why it's positive. Okay, so that's what we got so far. So remember, this reaction has small amount of acid, not a whole lot, because I will explain what would happen if you have a lot of acid. So we have small amount of acid. So when you have small amount of acid, it will immediately neutralize any type of negative charge. So this negative charge, whatever we just made, it will be immediately abstract the proton from whatever the amount of proton we have. So let's do this. So we have our so this is N. Oh, we gotta color code this. So this NHH CH3. Okay, so we neutralized the negative charge here. All right, so now so we had our base. So based on our instinct that we have learned so far, what is our next instinct is saying? So we're going to neutralize the positive charge on nitrogens. So let's do that. So our base, like anything that could abstract a proton, will abstract the proton. So it will neutralize the positive charge on nitrogens. So let's draw the intermediate. And this is called carbinolamine. Again, the name is not important. CH3H. Okay, so at this point, so we just made our BH plus again. BH plus again. So what would happen is, we know that nitrogen has lone pair, oxygen has lone pair. Now any one of these lone pair can again abstract the proton. But if nitrogen does it, that's basically going backward. So this reaction will be in equilibrium. So all of these steps. So we want to make something different. So let's say oxygen abstract the proton. Okay, so if the oxygen abstract the proton, what shall we be making? So we will be making OH. Okay, I'll make it. So oxygen abstract the proton. Now oxygen has 3 bonds, so it should be positive. And then CS3, CH3. Okay, now we got, oh no, I flipped the color. Okay, NCH3H. Okay, so what is our instinct saying at this point? So we still have our base, right? Base is there because your base has abstracted, it got neutralized. So in this case, what we should do, we should neutralize the positive charge on oxygen. So let's do that. Okay, so if we do that, let's say if we neutralize the positive charge on oxygen by removing these 2 electrons right here. Okay, so if the whole thing is gone, so look what happened. The carbon does not have octet anymore. So in order to maintain the octet of carbon, the nitrogen will immediately supply its lone pair to make carbon happy. Okay, so everything happens together. So immediately nitrogen has lone pair and it will supply that lone pair towards the CN bond. So what shall we be making from here? So we will be making CH3, C, CH3. Now we will have a double bond N, CH3, H. So we just made our water. And if you remember, our base is nearby as well. So we had base before. And you see here, the nitrogen right here has 4 bonds, so it should have a positive charge. So what is our instinct in saying? So far what we have learned, every time we see a positive charge, we should try to neutralize the positive charge on the nitrogens, right? So how can we do it? We give away our proton and base would immediately abstract the proton, right? So let's do it. So let's do this one. So this abstract a proton and we will bring those two electrons towards nitrogen. So we will make our imine CH3 double bond and CH3, and this is our product. So this is our product imine, and then we regenerated BH plus. So you see we regenerated our BH plus. So you need a catalytic amount of proton and not a lot of proton. So here is why. So this reaction is pH sensitive. So this reaction is pH sensitive. This reaction is pH sensitive. So I will explain why. What happens? So scenario 1, when pH is too low. When pH is too low. So what happens when the pH is too low? You have a lot of proton. You have lots of proton. So all of those proton. So when you have lots of proton, the nitrogen on the amine will not be available to attack. The nitrogen on amine will not be available the nitrogen on amine. So I think I should say the lone pair to better way to put forward, the lone pair on nitrogen will not be available to attack on the carbonyl carbon. So you see the step 1. So you look at your step 1. What happened in the step 1? The lone pair on nitrogen is attacking on the carbonyl carbon. So if you have too much proton, so this is what would happen. If you have too much proton, all of your CH3 and H2, when you have too much proton, Hb plus, you will immediately make this. So you're going to make this ammonium salt with CH3H and then plus. So the lone pair is not available. So the lone pair on nitrogen is unavailable, right? So this can't form a nucleophilic attack. So can't do a nucleophilic attack. Okay, so now you see why we can't have too much proton. Next question, when pH is too high. So what would happen when the pH is too high? When pH is too high. Okay, so when the pH is too high, a couple of things would happen. First, so you noticed we are neutralizing the O negative ion, right? So you can't neutralize the O negative ion if there is not enough proton. Remember, pH is when things are above 7, then you're not going to have acidic proton. So you cannot neutralize it, right? So the only thing that would happen is it'll go back, it'll kick out this group back again. So you can't do this reaction. So when pH is too high, the O negative ion on tetrahedral intermediate cannot be neutralized. And also, you noticed here from carbinolamine. So this molecule here is carbinolamine. Okay, so the carbinolamine, the OH cannot be protonated to be removed. So those are the two things that won't happen. When the pH is too high, there won't be proton available, so that you cannot protonate your OH. As a result, you cannot remove the water. So a couple of things that would happen when the pH is too high. That means no H plus ion available. So which means we can't neutralize the O minus ion on the tetrahedral intermediate. Okay, and also we cannot protonate the OH group of the, hopefully my spelling are correct, carbinolamine intermediate. Okay, so you noticed here, in order to proceed the reactions, the OH group here must be protonated. So if your pH is too high, you cannot do this. So there is a sweet step. So the pH, the rate of this reactions, so you can see here around 4.5 is the highest. So this is the rate of reactions, and this is pH. So you notice in this case, when the pH is around 4.5, this is where you get the maximum rate. If your pH increases than 4.5, the rate of reaction drops dramatically. If the pH drops than 4.5, so the rate of reaction drops dramatically. And this is why we said in the reactions that you need to have a trace amount of acid. The pH has to be just perfect. All right, let's stop this video here.